Okay, hello everyone. Welcome to the week 6 lecture about recursion in Python. So we do the recursion part 1 for this week, and we do the other part next week on lecture 7. So the C++ version of recursion is covered in Computer Science 165 and 210 at DVC. Not sure if 165 is, but I'm sure 210 is. So let's get started. The study goal is what is a recursion and how many kinds of recursions are there? What is a recursion like? And what is recursive leap of faith? Okay, so recursion. Recursion is the trick that let the function call itself, whether directly or indirectly. So I have an example recursion. So define recur. If n is less than 0, return 0, else recur. So every time a recursive call takes a smaller argument. So usually when you have x and it will be like smaller version of the problem, it just becomes maybe x minus 1, maybe x 4 divided by 10. Yeah. So does the recursion open different? Yes. Why? Because every time you do the recursion, you do a recursive call, which is actually a function call, but it calls to itself, the function itself. So we do open many new frames when having the recursion, and because they are calling the function itself, because the function itself, sure is a function. So when you call the function, do recursive call, it will open a new frame, also created by this function, but like taking smaller arguments of the input. Yeah. So okay. So types of recursion. Recursion is we have 3 types of recursion, which is first is non-aggregate recursion, also known as tail recursion, and single aggregate recursion, which is the common recursion we will talk about and we will use for the rest of the lecture. And they have multi-aggregate recursion, which means we aggregate more than one time. So it's also usually called tree recursion. We will talk about that for the next lecture, and we will talk about the tail recursion and the single aggregate recursion for this lecture. So, okay, why is it tail recursion? Why is they called non-aggregate? You surely know about it very soon. Tail recursion is the recursive function that has only base case and recursive call. Like in other words, it does not call non-aggregate recursion. This is example. Define recur x if x mod 13 is equal to 0, return x, else return recur x minus 1. So this is the base case of the recursion. Base case means that when I call this function again and again, like it must have some point that you have to stop the recursion because recursion is actually kind of loop. And for some special case, you have to stop the recursion. Otherwise, the recursion will go again and again, and you can't stop that, and you will crash the program. So the base case is very important and is also usually a point of solving a recursion problem. Base case is used to stop the recursion. And if you do not use base case, it would be an infinite recursion. Yeah. And the next part is the recursive call. When the function calls itself, call of the that call is called recursive call. So recursive call is usually the very end of the recursive function, and is used to solve the problem by try exploring the solution of its smaller version. Yeah, so that's why we're taking smaller arguments into recursive. If you are if you keep passing the original output input x or maybe bigger than x into the recursive function, and you are not going to to hit the base case. So you try to make the problem arguments bigger and bigger, so it's far moving farther away from base case. So which means you cannot solve the problem, especially when you put the original. You just simply just call the origin again and again. So usually we just looking into the smaller version of a recursion. Yeah. And so the tail recursion. Tail recursion is the last step of at this frame is the recursive call. It's usually where how is defined. Tail recursion, tail means that the very last step. So the very last step of the function or the very last step of the frame is the recursive call. And usually when you start a new frame by calling the function again using the recursion, in tail recursion, it will close the old frame, which means that usually like I had the return here, but there's nothing to do, nothing else because I don't aggregate here. It's nothing else. It's just the recursive call. And so recursive call it opens a new frame. But this is the last step of this frame, so it will close the frame as well. So, which means that usually when you run a tail recursion, usually you only have one or maybe two frames running at all the time. And the last step of this frame is recursive call. So it means stop the old frame and open a new frame. And why is it called tail? It's very usually, like for example, I have an image of a cat. I suppose we call the cat a cat function. We treat it as a function, and the body is the function body. And then the tail is usually called the tail call. The tail call, which means the recursive call is the very end of the function. And when you pass in an X here, it runs through the function body and it calls the tail call, it return to call the function again. And then you call that, enter the function again. And then you have the tail call again. Like tail is like the very last part of animal of the cat. So is also the same as like when I do the tail recursion here. Um, the last step is the recursive call. So which is very similar to a cat. Yeah. So any questions about tail recursion? Mm. Okay. So usually tail recursion don't do the aggregation by using like by itself, but I can actually do aggregation in tail recursion. Questions. Must I write return before the function call? In tail recursion, not really. But in single aggregate recursion, which we'll talk about it later, you must write return before the function call. Yeah, because tail recursion is actually just iteration though. It's usually just the iteration. So iteration, you don't actually have to return something. This is just like kind of my habit, like my coding habit. You don't have to write return at tail recursion. But you have to write it in single aggregate, and we'll talk about it later. Yeah. Okay. Got it. Sure. And okay. So how we do aggregation in recursion? Aggregation means that we suppose there's a broken glass, and then we find the pieces of glass and try to make it as an try to make it to be the original original type of glass, which means that before broken. So aggregation means that you have many pieces, and then you add the pieces up together to try to make it to a new try to make it to be the glass which looks like to before broken. So I have many pieces and I try to add it up together. This is called aggregation. So we can also do aggregation in tail recursion, although we don't do aggregation after the function call. So we can use nested functions. Nested functions we can insert the function into another function, and then you can try calling the function. We have a nested function inside the function, and then we recognize function and we try to call it by passing into our input and auxiliary variable, and then we can just try to run the tail recursion in this function. So for example, we here to find the factorial of an integer. So factorial means that when I do this 2 means 2 times 1, and 6 factorial means 6 times 5 times 4 until I hit times 1. So this is the factorial of an integer. For this part, we do nested functions inside a function, and then we can use the helper function to do the tail recursion. And we don't actually have to aggregate. Why? Because we do the helper function. We define helper function with the input of the outside function, and then we have the solution. Solution means that we may gonna return that. But how we return that? So the first thing, like before returning date, we have to accumulate the solution. To accumulate the solution, for the very beginning, we have the solution like just simply equals 1. And then every time when I recognize this helper function, and then I call this helper function, and then it goes into the recursion for the next step. And then we have the number input. If the number is less or equal to 0, which means the base case, means the number already deduct to 1. So which means that our solution is like we already have our solution, so that we just return it. And otherwise, we do the aggregation like this. So which means that solution just times every time times the number during so many steps. So we have 5 factorial, for example. So 5 times 3 times 4 times 3 times 2 times 1. And then for the first step, we have 5 as the number input. If we are not having this base case, this is the base case of the function. We are not, if we are, because it's 5, so we do not enter the base case. So we have the solution times the number. So solution is 1, like we're checking the variable solution is 1, and then it times 5 here, and then we call this function like the tail recursion again. But this time we deduce the number. We reduce the decrement the number by 1. So I will hit 4. So just times 4 for this step, and then we try to call the tail call again, and then you will have 3 and 2, etc., until you hit 1. So if number is less or equal to 1, so you just return this solution back. So this is how it works. So actually, how to back to the problem, how to do the aggregation. We don't do the aggregation in function, the recursive call in tail recursion. We will instead do the aggregation as somehow at a point like that. We will have a new line, and then we try to accumulate the function, try to accumulate the variable, the auxiliary variable, and then we will do the duplicate of the solution, and pass it into a new cycle of the tail recursion. So yeah, so any questions about it? Yeah, okay, we can do a demonstration of this. So this is, oh, so okay, so this is the Python tutor. We have this function. We try to find factorial 5. So go into the function. So for the first step, the function is like recognize the helper function, and then we just hit the function call of the helper function, and then we pass into the input and pass into the starting value of the auxiliary variable, which is solution here, which is the variable solution here. Okay, and then we goes into the tail recursion. In the tail recursion, we have the n is 5, so the if here is the base case. So we will skip the base case, and then we go to the solution times equals n. Yeah, so we will start accumulate the value into the variable solution. So we have solution times equals n. So it will accumulate. By now, for this first step, it will accumulate to 5. And then we hit the recursive call, the tail call. We hit the tail call, and then we reduce the input by 1, and then we duplicate the solution, or like in other words, you just like to pass the new value, pass the variable solution with the new accumulated value into the tail call and run the cycle again until okay, and then we'll go back into helper. So helper, this time solution is 5, and here we got n is 4, and then we accumulate again. So it will become 20. So we call it again, so it'll be 60 and accumulate 120, and now we hit the base case, n is 1. So for n is 1, return solution. So we just return this solution back to so many frames. Yeah. So until we return that to where the factorial function is called. So C will be 120. So this is how it works. I noticed that for every step, actually the frames here is closed. They are closed because the last step of the in their frames is the recursive call, and the recursive call opens a new function, and then there's nothing left there, so it will close the frames and start a new frame and try running that on the new frame. But when you return, just like we open it again and then throw the return value into it, and then just go past like a relay. Okay, so go past that. Yeah. So any questions about tail recursion for how to do aggregation in tail recursion? Yeah. Okay. So this is how tail recursion works when you try to. This is how tail recursion works when you try to aggregate. You're like create an auxiliary variable, and then to accumulate a variable in each frame, in each step, and pass it into the tail recursion to accumulate every step again and again until you hit the base case and you just return the auxiliary variable. This is how tail recursion works with aggregation. So what if I do simple aggregate, which means that we don't have to duplicate or we don't have to have an auxiliary variable. We just try to accumulate the variable, aggregate the variable, the values at the place where the function is called again. Yeah. So we do single aggregate recursion. So here's a very famous example about a queue example. So suppose you are trying to visit the London, maybe one of the museums in London, and then you are having a line in front of you and you have a queue, and you try to know how many people ahead of you. So when you wait in line, want to know how many people in front of us, like we're in a rush or something. And then we'll ask the people in front of us, how many people in front of you. And the people who asked also don't know, also does not know. So he or she will ask the person ahead of him or her again. So they also ask the people in front of them. And then so people who have people in front of them they will try asking people ahead of them and try to figure out how many people in front of the person in front of him. Yeah. And then they pass the question from the very end of the line to the beginning of the line, where the first person in the line. Yeah. And the first one is asked about the question, how many people are in front of him. He will say, oh, I'm the first one. So he will answer with 0, meaning he's the first one and there's no one ahead of him. And then people will pass the answers back. When people behind him, for example, the second people, the first people say 0 people in front of me, and the second people will say, oh, I have one person in front of me, and the third people will say, the second person tell me that he has the second person tells him the third person that there is actually only one person in front of the second person, and then the third person will say, oh, okay, I have 2 people in front of me. So every time when I hit the so every time when I find out when the people receive the answer, he will pass 1, like including himself, to the back, and then we pass the new answer to the person behind them, and then so on and so on. And then when the person in front of us is told the number, he passes 1, like, and tells us the result. Suppose the person in front of us knows the answer, and then he passes himself into the answer, and then return the new answer to us. So then we also add, like, so that we know how many person in front of the person in front of us, and then we will eventually know how many people are in front of us. Yeah, so we get the number. Okay, and single aggregate recursion is like the common recursion we will use for this lecture. And then we have the old example to find the factorial of an integer. So we have factorial number, and if number is less or equal to 1, it will return 1, or else we would return number times factorial. We do the aggregation. Yeah, this is how we do the aggregation. So this is the base case, which is usually like only for this situation. Suppose factorial is 0 is 1, factorial is 1 is also 1. And this is a base case, like, because there's no number ahead of them that also apply into the recursion. Okay, questions? What's the reason of using nested function in the last example? Okay, so so using the nested function is because we are not going to do the aggregation in the factorial because we have only one input here, and you want the auxiliary variable, and you want to duplicate the auxiliary variable in the function. So obviously you can have the auxiliary variable in the outer function because you only receive the input. You only receive the only one input of the outer function. So that's why you use nested function, because in the nested function you can use the auxiliary variable. So that is why we have to use nested function. Yeah. And okay, let's go back to the yeah. So this is the base case. Base case is used to start the recursion. So this is the base case of the factorial. And then we have the function call factorial number -1. So every time, suppose we do factorial 5. 5 is 5 times 4 times 3 times 2 times 1. So every time I have factorial 5, which means that it's 5 times factorial of 4. So we do this recursive call, and then do the passing the smaller version of the argument, and then times like, because this is how factorial works, and then you pass into the number times the number with the factorial, and this is the recursive call. Recursive call to make the problem of a smaller version of it. And then this is the aggregation to combine all the smaller results together and aggregate recursion. The last step of this frame is the aggregation. Like, suppose I have the frame and I have the recursive call here, and then the last step is actually like that's something, maybe a number A plus the recursive call. And then when you hit the recursive call, you have to evaluate what the function call returns. So you will open a new frame, but at the same time you keep this frame opening because you still have a addition, because you just leave that and open a new function frame. So when you are running this function frame here, you will leave the old frame opening, and then until the new function frame returns a result to here, so that you can do the addition. So you get the number, maybe a number or string something, and then you will end the old frame at this time, because you do all the things. Yeah, you do all the things because the addition is the last step, the aggregation is the last step of the frame, and you keep the old frame open when opening a new frame. So it's like, as what I just say, open a new frame, you keep the old frame opening because you still have something, the aggregation, you leave the aggregation undo. So you have to evaluate the function call first, and then you return the number from the new function frame to the old function frame, and then you do the aggregation so that you get the result, and until here you will end the old frame, and then pass the value to where the function is, the recursion function is called. Yeah. And how you do the aggregation? You will use recursive leap of faith. Recursive leap of faith. Recursive leap of faith is to believe that a recursive function works well, and then returns the correct answer, correct results. So it's like when you're doing the aggregation, you assume that the recursive function returns the correct but smaller version of the result, and you're thinking about a proper instance to combine the smaller version of the result with some operations according to a proper instance. Yeah, and all you have to do is like to combine the result at the frame with the correct output of the smaller version of the problem, so that the result can be the result you want. So I'm doing an example here. Example, recursive leap of faith. It's kind of like a concept of how you do the aggregation. So define factorial number, also the same thing. So you do if number, this is the base case. Yeah. And how we do the recursive call. Suppose we know 5 factorial is 5 times 4 times 3 times 2 times 1. And this is the factorial of 4. So for this time, you know that like this is the function of the factorial. This is how is that? Yeah. This is the recursive call of the factorial function, and we are passing a smaller version of the problem into the recursive call. And then you have to assume that the function you wrote already returns a correct answer. Suppose like I already returned 4 factorial 4, I think is 24. And then all you have to do is like how you do how we do factorial. Like according to factorial, you're doing like we have to times the number we currently have to the returned output. So we already assume that the function um, we try to implement already works very well. And then all we have to do is to combine the result from the smaller version of the problem to the number, to the current number we have, or maybe something like some other operations to achieve your goal, to achieve your purpose. Yeah. This is how recursive leap of faith works. So any questions about this? Okay. So here factorial 5 is the factorial is 5 times the factorial 4. You have to believe that factorial 4 can return the correct answer of for this. And that's how we define factorial, and that's how we think factorial will work. Yeah. You have to believe factorial of 4, the function can return the correct answer, and then think about how to aggregate between your input or maybe other things with the result of the recursive call. Yeah. So back to the queue problem. When we wait in the line, want to know how many people in front of us. So try to think about the structure of the recursion and to think about what the steps stand for. So for the first two lines, we ask the people in front of us, and they also ask the people in front of them. So this is the recursive call. Recursive call is like I try to smallerize the problem to make the problem smaller. So we can try to figure out maybe a smaller problem can return a result, and we think about how the result can be our final result. So we ask the people in front of us, and they also ask people in front of them. So when the first one is asked, it's set 0, it's base case, because he does not have people in front of him. So he can easily know the result, can easily know the solution. So at this point, we have the base case, and then we will return the smallest version of the problem, and then we try to return the answer to maybe the bigger version of the problem and see how to aggregate. And when people behind him and at one pass a new answer to the person behind them is the aggregation. Like every time the people will will add themselves to the answer and then pass the answer to the people behind them. Yeah. When the person in front of us is told a number, he passes 1 and tell us the result. This is the recursive leap of faith. Yeah, we have to believe that the answer that the person in front of us already have the correct answer. We'll assume that the answer is correct, and then we will try to aggregate the result with the output from the smaller version of the problem, and then you get the final result. Yeah. So here is the practice to do the recursion. Yeah, the recursion. Remove all the even numbers using recursion. So the input is this number, and the output is the number that you already kick out all the even numbers. So let's have 15 minutes to complete this fill in blanks to try to make it a recursive function to have the input and output. Yeah. Oh, any questions about this? About the recursion, the recursive leap of faith. So why I have to do the return in single aggregate? That's because we have to pass the value back. When you find out the output of a smaller version of the problem, and then you will aggregate it with the input or something else, so that you can make it like the output, make it like the output that is which we will want. Uh, we have to return that to the function to which represents the bigger version of the argument of the problem. Yeah. So we'll talk about it in at 8:50 p.m. Yeah. If you have questions about the lecture, just you just type at the chat box. So guys, I wrote down the hints on the slides. I think they would be very be of good use. So we have five, wait, yeah, 5 minutes left. Yeah, we have 1 minute left. Okay, so we're gonna talk about this problem. Um, we already have the no even function written in iteration in lecture 4. But using while loop is very complicated, and if you're doing 2 while loops, that would be very easy to understand. But otherwise, you're doing 1 while loop, it will be very complicated, I think. But for recursion, it's actually not that hard. So we'll talk about this. Um, so how we're gonna approach the problem? Mm, so we have to remove all the even numbers using recursion. So which means that um maybe you can just like try to we have two um we have two conditions. The first is when I do kind of like 4 divided by 10, I'll get the last digit. If the last digit is odd, which means that we have to keep it. And the even digit, if that's the even digit, we have to abandon it. So if that's even, it's just simply if we do the first step because that is even. So we will get this such kind of number and 4. So we have to like abandon it, which means that we just don't have to aggregate it. We don't have to aggregate it. So we have to put this back to the recursive function, and then to try to run it, to try maybe there are other even numbers that should be thrown out. So for here, else if the n so should be mod 10 to get last digit. So just mod 2 again to try to see if there's 0. Or you can just do n mod 2. Yeah, because usually to see if the last digit is odd or even, you just do mod 2. Yeah. The eraser. So for here, so for the first aggregation, we do n mod 2 is equal to 0. And I return no even and n4 divided by 10. Yeah. So we just throw this number into the recursive call and try running that again to throw out other even numbers. So the next step of it is like, okay, we got this number and this is odd. So we also do the like mod 10, we get the last digit 1. We have to keep this. So we just plus this kind of when you do the odd to aggregate is like the number like I will throw this number again into the recursive call, and then we try to aggregate plus 1. Try to aggregate by having the return result and then plus 1 to get this. But it will be 5, 20, 1, 4. That's not correct. We have to get 5, 20, 1, 3, and get 1. So which means that we have to times the number by 10. So you get 10 times this. But we are not going to keep all these numbers. We will have to throw it into the recursive call to find out the correct solution. So which means that from here we have no even, and throw this part of the number into the recursive call again. So for here we actually apply the recursive leap of faith. Why is that? Because when you don't know how to do the aggregation, you will assume that this function already works very well, already works fine, and return the very correct answer. So what you have to do is like to try to make the recursive call and do the aggregation. And then for here, you have to pass in a smaller version of the problem. For here, I do n mod 10 to get the remaining part of this number. Like I already figured out this is odd number. So then I will still throw it into again to try to kick out all the even numbers. But before doing that, before doing the aggregation, we have to assume that this function call already works very fine, already works very well. So we can just simply write this down, pass in the smaller version, and then we do the aggregation with the function call and the input. Yeah. So for here, for this case is 1, but for other case you do n mod 10. So for this case, for the else statement, which means there's only odd or even numbers. So we return 10 times no even, and then n mod 10 plus n. This is n4 divided by 10, and this is n mod 10. This is for else. Yeah. So the last part is base case. The base case is like I'm actually for divide again and again until I have all this number so to be 0. So when I for divide by 10, all the digits for divide by 10, I will have 0 left. So which means that when I receive the output which is 0, means n is 0, and I have to return 1. Maybe 1, maybe x, n, but I will return 0. So when I return 0, you have to figure out sometimes when you do plus, it's reasonable to have 0. But when you do the aggregation to be multiple, it's better to have 1 because 0 times everything will be 0, which means that we have nothing else left. But for here, which makes sense though, because for here the aggregation is plus. So for here we just return 0. So the function looks like this. So function looks like if n is less or equal to 0. So this is the base case. Return 0. And then for here is like for the condition, it is like so go out the even by simply not and yeah, and this is the last digit is odd number. Yeah, and you find out then 5 recursive assume that no even well the smaller version of the problem. Then find the way to find the way to aggregate with the smaller result with input. So for here, I find a way of to aggregate is like I have found out no even for this one already returns the number. For example, I'm doing 5. I'm doing this one. So I already found out 1 is an odd number, and I already assumed that so for the output, like already assumed that is something that's 1, and this is the correct answer. This is the correct answer, and I know that when I do the recursive call, no even, I already know that this will return 5131. For the output, I already assume that this recursive function call will return the correct output, and all I have to do is like try to aggregate it by 10 and then add 1. So it will become 5131 5131. Yeah. So that is how to solve the problem. Yeah. Any questions about it? Oh, okay. So I know that this recursive function will return the correct output. And all I have to do is times 10 and plus 1, and it will become the answer I want. Yeah. So this is to assume the function returns correctly. This applies recursive leap of faith, and you do aggregation with recursive leap of faith with the input, and then you get the answer. So that's how to do the aggregation. Yeah. All right. I think that's it for today. I'm sorry, guys. I didn't actually do the presentation very well. I think if you have any problems, any questions about recursion, just please reach out to me. As long as you have questions about it. Yeah. Okay. I think that's it for today's lecture. Yeah. It's a bit complicated. No, it's maybe. Yeah. You're welcome. Try to reach out to me if you have any questions about, especially recursive leap of faith and how to do aggregation. Usually for tail recursion, you will get that if you attend a course at Berkeley, you will attend it at the end of the semester. You will have that at the end of the semester because they do recursion and tail recursion at very different places. So I was thinking tail recursion is actually very simple because it's very, very similar to literally iteration. But for single aggregate recursion, you have to think about recursive leap of faith and try to aggregate and try to assume the recursive function returns the output, which is correct. Yeah. All right. Thank you, guys. Thank you very much. Yeah, it's hard to explain a little bit. Yeah. But if you have anything that confuses you, just reach out to me immediately. Yeah. Okay. All right. Thank you. Have a wonderful week. Yeah. Okay. Yeah. Thank you. Okay. Good night.